So, complex number review. Why are these so important? Well, they're fundamental to how we deal with phases, and that's what we're concerned about now, because we're looking at steady-state sinusoidal analysis. So recall there are actually three ways that we can describe a complex number. There's first the Cartesian form, x plus jy, or in this case z equals r plus jx. I'm using the kind of terminology that we'll meet in this course. So z would be impedance, r would be resistance, and x would be the reactance of either an inductor or a capacitor, or combined together in a series or parallel circuit. So that's the simplest way of looking at it, and if we look at it graphically, we can see that what z describes is really a position on the complex plane. In other words, r plus jx are the coordinates of our complex number, or our point as described here. M, the modulus or magnitude, is just the distance to the point in question. So by using trig formula, we can easily get from statement 1 to statement 2 here, since r is just m cos theta and x is m sine theta, or sine phi in this case, not theta, and that's simply finding that as a function of this and the angle in between and so on. So those two I think are fairly straightforward and understandable, intuitive in other words. This one, which unfortunately we tend to use rather more than the other, is not so intuitive. Particularly the e to the j phi here really doesn't jump out of the page as being something that's very obvious. But actually what we're really talking about here is the magnitude and the phase expressed as e to the j phi. An Euler's formula will enable us to get between these two versions of a complex number. Personally, whenever I deal with complex numbers, I find it very worthwhile to remind myself of the graphical procedure here, or the process, the description of it, of the complex number, as a point on a complex plane. And really, what we're talking about here is simply a two-dimensional vector system, where the j separates the real part from the imaginary. In other words, the j acts as an operator to keep the phase all organized. And this complex plane is named after Argon, so it's known as the Argon Diagram. Argon was a French professor. And here's the comment I just made, that complex notation just describes and organizes what amounts essentially to a two-dimensional vector. And j maintains the 90 degrees between the quantities r and x. Three ways of getting at the phase from a knowledge of the r, x and n. Now I've listed them all here. The one we tend to use most is this one. Phi is arctan, or tan to the minus 1. At is the mathcad way of saying this, but it's the same as tan to the minus 1. Imaginary over real, x over r in this case. Or if we knew the magnitude, the m, or the magnitude or modulus, then the arc sine of x over m, or the arc sine of, or arc cosine of r over m. So any one of those can get us from the two quantities involved to the phase. Magnitude or modulus, we use Pythagoras Theorem. In other words, m squared equals x squared plus r squared. Notice, since we're just talking about lengths here, if x was negative, in other words, if this point was down here, we'd still have exactly the same expression, because what we're talking about are distances, if you like. So r squared plus x squared square root of gives us m, wherever we are in any one of the four quadrants. Here we're in the first quadrant, this would be the second quadrant, the third quadrant, and the fourth quadrant. Now, I mentioned frequency response here. We haven't met this yet, although we have introduced the idea of frequency. We've looked at things at 60 Hertz, but quite often what one is really concerned with in a filter is the frequency response behavior, and this is how the gain of a filter or an amplifier changes as the frequency changes. You've all met the idea of frequency response in a sense of high fidelity amplifiers, and quite often with amplifiers you can change the bass setting or the treble setting, and all you're doing is altering the frequency response using a filter to either amplify the high frequency or attenuate it, or do the same to the low frequency. And so frequency response is something we're going to be very interested in as we move into electronics, particularly if we're concerned with amplifiers. And we'll be concerned with the gain or attenuation of the amplifier or the filter. And also we may be very much concerned with the way the phase changes through the